Hello everybody. Today's video is talking about U-substitution and definite integrals. So I've already talked about indefinite integrals, which are the collection of all of the possible anti-derivatives of a function. Definite integrals are a bit trickier, but also more useful. So let's go ahead and jump right in. First thing I want to talk about is U-substitution. This is a fairly useful technique to find integrals. So, quite often when you get an integral, it's going to look pretty ugly. So you could use U-substitution to try and find some simpler way to deal with it. So it's similar to the chain rule, where you want to look for an inside function, but you also need to find its derivative, which hopefully the derivative you'll be able to find on the outside. All right, that sounds slightly confusing. So let's take a look at an example. So we have this integral here. This is not a pretty one to do because you have a function inside of an exponent with another function on the outside multiplied. Now, you could calculate x squared plus 1 to the 6th, do that all out, and combine things and do it that way. Or you could use U-substitution. All right, so the most interior function is the x squared plus 1, which we set that equal to u, hence why it's called U-substitution. All right, now you need to find its derivative, and this is where the du dx things come in a little bit more. So the derivative of u is 2x times dx. All right, so derivative on this side is u, derivative on this side is 2x times dx. The one, when you take the derivative of it, is a constant, so it goes to 0. All right, so now that you have the u and its derivative, you want to be able to get rid of all the x's using these two things. All right, you should only ever use the du once. The u you can use multiple times. All right, so if we look for it, we could see, well, the u is easy to find. The du is 2x dx, so we take the 4x dx, put them over here. But we don't want 4x, we only want 2x, we have to pull the 2 back out. So that's our du. So if we substitute it in, we now get this indefinite integral here, which looks much easier to deal with. So you use your basic power rule for integrals, add 1 to your exponent, divide by it, there you go. Now, keep in mind, this is u. We don't care about u, we care about x. So you need to substitute what u was back into your equation. So you get 2 over 7 x squared plus 1 all to the 7th plus c. All right? So that's an example of how to use U-substitution. You can do stuff similar for when you're taking the derivatives, but it's not quite as necessary. You can just find your interior, exterior functions and do some less type of stuff. All right. Now, let's go ahead and take a look at an actual example for you to try out. So I want you to find the derivative of, or integral of this function here. All right, hopefully you found u is equal to this here. All right, go from here. All right, if you're having difficulty, you should be able to find the derivative of this, and you should get something that looks like this. Okay, now you should notice that this does not match exactly what we have up here in the top. So you want to get this to look like this. So you multiply both of these by 6, but if you're multiplying them by 6, you have to divide by 1/6 as well. That way it still stays the same problem. But now this does look like this. So go ahead and go from here. All right, so you should just substitute it in, and you'll get this here, which when you change it to power notation, you get this. So go ahead and try from here. All right, hopefully you're getting something that looks like this. Kind of ugly, deal with your fractions, and make sure to substitute your u back in, and here is your final indefinite integral. All right? Keep in mind this is a fairly useful technique, and it is one that you should know how to use. All right, on to definite integrals. So you can view these both graphically and numerically and algebraically. In our class, I'm primarily going to focus on the algebraic side, but I want you to understand the graphical as well. So when we talked about derivative, that was always talked about the slope of our function. Well, integrals also have a graphical interpretation along those lines, but instead of being the slope, it's the area underneath. So we talk about the definite integral, it's the area under a curve, which is between the two x values that you're given. All right, so I'm going to show you an example to this quickly. But in order to do this, well, most of our functions don't have a pretty nice shape where you can just measure it out easily. So to approximate it, we use something called Riemann sums, which, let's go ahead and take a look at a quick example of what that looks like. So if we have this function here, and I want you to find all this area. Well, I don't have any nice functions that tell me exactly what this does, but I can approximate it by putting in squares. What you see here is a left Riemann sum, okay? So what you do is you go to group this up into categories. So you see -1, 2, 4-ish, wherever you decide to put the splits, all right? But they should be equally spaced. And on the left of each box, go up to the height of your graph, and then finish off the box. Here, go up to you on the left, finish off the box. Here, go up, finish off the box, and so on. And now the approximated definite integral of this is just the sum of the areas of all these boxes. But you'll notice that, well, this box is going to be underestimating it. This one's way overestimating the area. This one might be about right, and this one's probably overestimating a little bit. So you can see that this isn't that great of a technique. But if you cut your box sizes in half horizontally, well, this box that's really overestimating, well, the second one's height would be here. So the overestimation would be cut off a lot. So by having smaller and smaller splits on the x-axis, you're going to get fairly accurate representations. Now note that I said this is a left Riemann sum. If you do a right Riemann sum, well, for every interval, you go on the right, go up, and then finish off coming backwards. All right? And then, so like this one would be up here, and so on and so forth. There's also a midpoint where you go to the middle of the interval, go up to where it is, and go the side to side for every interval. So those are the two and three ways that you can do the Riemann sums. Keep in mind, the more boxes you have, the more accurate it will be. But we always do the splitting on the x-axis, and we always just go up to the graph. Nothing else in between. All right. So that's the graphical interpretation of a definite integral. Let's talk about the algebraic interpretation of it. Well, you can write it as an integral from a to b of f of x. All right. Now, we've already done the integral of this, and there should still be a dx here. So we've already done a definite or indefinite integral of this, which you still use that same thing. So you will find the indefinite integral, and then you will evaluate it from a to b. So what you do is you find an antiderivative, plug in the larger value up on the top, subtract the smaller value on the bottom. All right. Now, if it just so happens that this is bigger than this one is, well, you'll just get the negation. It'll still come out to the same numerical version, just with a different sign. And this is something called the fundamental theorem of calculus. All right, so let's take a quick look at an example. So let's say we have this integral that we want to calculate. Well, you find the antiderivative. So you get x minus 1/3 x cubed plus c, and evaluate it from 0 to 1. Now that is general notation. You put a line afterwards to show that you still have bounds on it. So now you evaluate 1, and then subtract it when you evaluate at 0. So you get this equation here, which when all comes out, the 2/3 is your final answer. Now note something. You have plus c minus c. The c's are going to cancel out, so when you're dealing with a definite integral, you don't need to include the plus c, because this is going to disappear regardless. Because it doesn't matter how much you have at the starting point, because you're only looking at the difference between the starting point and the ending point. You don't care about where you were beforehand. All right? So second exercise. So let's say the weekly sales of your t-shirts is decreasing by 5% per week, and it's currently selling 20 of them, or 50 of them, sorry. How many shirts do you expect to sell over the next year? Well, you could calculate every week how much I'm expected to sell. That could be a bit of a pain. So this is one of those situations where finding a definite integral will actually help. So first of all, you need to find your formula. Was this a continuously decreasing function? So probably the PERT will be the most useful. Which you have your present value, which is 50. Your rate is negative 0.05, and t is in weeks because that's what the time is counting as. All right. Now, we want to find the integral from 0 to 52 of this function because there's 52 weeks in a year. Well, basic antiderivative of this, the exponential stays the same, coefficient in front stays the same, and you just divide by whatever the derivative up here is. All right? That works as long as it's a straight linear up there. Now go ahead and evaluate this from 52 to 0. And you should get something like this. All right? So your final answer, you should get something of the lines of 925 shirts over the year. All right? So that's an example of using a definite integral in an applied situation. Hopefully you've learned something. I'll see you in class.